Hi, I'm Prakhar, and today I'll be presenting our work, an empirical investigation into benchmarking model multiplicity for trustworthy ML, a case study on image classification. What is model multiplicity? We make many decisions when designing a machine learning pipeline. For example, which dataset we are going to use, how are you going to split it between train and validation, what learning algorithm are we going to use? What is the architecture of our model? What is the batch size? What is the learning rate in our training, etc. We eventually combine these choices along with multiple forms of randomness. For example, the weight initialization, the data order, augmentation, dropout, etc. to actually train the model, which we then benchmark on some test dataset. We use the performance of the model on these datasets to judge the quality of our setup. However, due to over-parameterized nature of deep learning, not every choice we make is unique. For example, we could have trained on a different dataset and still achieved the same test performance. We could have trained the model with a different batch size and still achieve the same performance. More generally, if we were to combine all the decisions we make into what we call the overall training setup, there are many different training setups which would all create different learned models, yet they perform equally well on the test dataset. This existence of multiple models that have different underlying decision boundaries but look indistinguishable on a benchmark is called model multiplicity. But if they have the same performance, why care about multiplicity? That's because measuring just the accuracy of the model is not enough to judge its quality. We care about many other aspects of the model behavior. For example, fairness for various demographics, privacy protection against information leakage, robustness to distribution shifts, etc., commonly studied under the umbrella of trustworthy machine learning. And while different training setups might have the same accuracy, they can still have wildly different trustworthy metrics. For example, fairness. Modern multiplicity gives us an opportunity to choose better models without losing the original utility of the training setup, and is an important step towards creating well-rounded and trustworthy systems. In this work, we attempt to first create an empirical language to benchmark and study multiplicity, specifically for a classification setting. We go on to actually benchmark image classification across various trustworthy metrics like fairness, robustness, privacy, and security, and highlight some interesting trends. Finally, we investigate the true potential of model selection and show that even though model selection can indeed help us choose better models for certain metrics, it still might not address lingering multiplicity in other unseen metrics. We'll start by first defining an empirical language to talk about and study multiplicity. We start by defining a new class of metrics which we call accuracy under intervention. Imagine a scenario where we want to study the impact of changing batch size on a model's adversarial vulnerability, its fairness, and its generalization capabilities. While we can measure all these properties with different metrics, they are unfortunately not comparable, which makes it impossible to get a complete picture of how batch size impacts various trustworthy aspects of the model. Instead, we propose translating these metrics into accuracies under intervention, while making sure they represent the original metric. For example, instead of measuring the minimum perturbation distance required to flip the label of an image, we can instead measure the accuracy of the model under attack from an adversary with some distance budget. While these accuracies are clearly not a replacement and do lose some information, they allow us to make certain blanket statements about the overall dynamics. For example, we can see in this toy setup, the changing batch size has a potent impact on the model fairness and a noticeable impact on OOD robustness. But it does not really impact the adversarial vulnerability of the model. Such a comparison can allow us to extract trends across different metrics that were previously missed. Next, we introduce multiplicity sheets, a simple way to record the model performance across various training setups. We have three different levels of readability in our multiplicity sheets. First, we record all raw scores to make sure no information is lost. Second, we measured the overall variance in scores across every axis to highlight and capture certain trends in the performance. Finally, we capture the overall variance of the metric at the bottom right in an attempt to compress the overall multiplicity into a single score. Note that these multiplicity sheets can be created for any metric. However, we focus on accuracy under intervention in our paper because it allows us to make comparisons across different multiplicity sheets, something that would not be possible if the metrics were not comparable. After defining the accuracy under intervention metrics and the multiplicity sheets, we performed two detailed case studies on image classification across many different sources of multiplicity as well as many different metrics, that is fairness, robustness, privacy, and security. Due to the time constraints of this presentation, I would not go into those case studies, but please check our paper if you're interested. Finally, we'll talk about some limitations of model selection. Till now, we have worked under the assumption that model selection allows us to pick better models. While that is partially true, we have not yet really tested how well do these selection translate to unseen settings. To understand how well does our model selection generalize to other unseen trustworthy metrics, we perform the following experiment. First, let's define how we do model selection. We train 45 different models by changing various hyperparameter values, optimizer choices, architectures, random seeds, and so on. We then measure the fairness, robustness, privacy, and security scores, all measured as accuracy under intervention, and choose models that are present in the top K% of all these metrics. In other words, we only choose models that are in the top K% in terms of fairness, and top K% in terms of robustness, and top K% in terms of privacy, and so on and so forth. Once we have selected these models, we then simulate unseen trustworthy failure cases by defining mildly different setups from measuring the same 4 trustworthy metric. For example, instead of fairness across various racial groups, we'll now measure fairness across various age groups. The attempt is to show how well would a real-world pipeline which incorporates model selection fare against unseen trustworthy challenges. We plot the score of all 45 models before any model selection, after selecting models that rank in the top 75% of all metrics, and after selecting models that rank in the top 50% of all metrics, respectively. While we do see a reduction in overall variance of scores for fairness, the leftmost graph, and security, the rightmost graph, we also find that the range of multiplicity has not really changed for both robustness and privacy, the middle two graphs. This highlights that while model selection under multiplicity is important, it is not the final answer to the problem of multiplicity, and more attention needs to be given to a fundamental exploration of multiplicity. Finally, we'll summarize the main takeaways of our work. We proposed a new class of metrics called accuracy under intervention and a new way to record model performance called multiplicity sheets, both of which were an attempt to provide language to talk about and study multiplicity. We performed detailed case studies on how to use our framework and the language, and we even extract various interesting trends while creating this benchmark. Again, we didn't really cover this in our presentation, but do check out our paper to see the actual benchmark study. We ended our discussion by highlighting the limitations of model selection and raised the problem of its generalization to unseen trustworthy settings. We believe that a more thorough investigation into the causes and sources of multiplicity is required to truly address these concerns. Thank you.